Hello, and welcome to my final year thesis video presentation and demonstration. This video will showcase the work I've carried out over the past year involving in my thesis, and I'm very excited to share it with you all. My name is Christopher Weir. I'm a final year student studying in National College of Ireland. I'm studying data science and my core specialisation is BSH DS4. So the title of my project is Beyond the Beautiful Game, leveraging clustering and generative adversarial network techniques for Europe's top football leagues. So the project overview. So what is it? Well, this project is based on a machine learning model. Generative adversarial networks, or GANs, are used in order to utilize a statistical approach to the tactical side of football. This model will give unbiased, clear pinpoint indications on where teams need to improve in their on-field play to compete and challenge with the best clubs in world football. So who is it for? This model mainly targets that of managers, coaches and club owners, as well as the analysts and sporting directors within clubs. So what does it do? Well, data with over 75 variables highlighting different areas of a team's in-play data across an entire season is normalized to per 90 minutes. These metrics are read into a k-means and hierarchical agglomerative clustering model. This model groups statistically similar teams together and assigns labels to the teams to differentiate teams in each cluster. The generative adversarial network model takes this data as an input, split into teams from the best cluster and the rest of the teams. The discriminator takes the best team's data value as 1 and the rest of the team's data value as 0 and is trained to differentiate between them. The generative model then takes the rest of the team's data as an input and generates synthetic data to pass to the discriminating model, so when the discriminator reads the new data, it assigns it as 1. This model takes the high-level relationships and structure between the data points from each team into account, which is what gives this model such an advantage. So how can it be used in a business model? Well, as previously stated, the model can be used by managers, coaches and club owners, as well as the analysts and sporting directors within clubs. This model can be used by managers and coaches to understand their team's strengths and weaknesses, pinpoint where they need to improve so that they can begin to tweak and shape their tactics around these weak points. It can be used by club owners if they are not happy with their manager's performance and want to look into the market for a new manager. They can utilize the model to see where other teams are stronger in their weaknesses and approach the managers of these teams. It can then be used by analysts within the club as an additional tool for their analysis reports on the game and to report back to the manager. And finally, it can be used by the sporting director who leads negotiations of players to sign for their club by understanding the profile of player the manager wants to sign, understanding how he may fit into the system and improve certain weak points in the current system to understand if team negotiations are worth going for or not. So how does it differ to models already in production? Well, as far as literature reviews have gone, as well as general knowledge of the type of systems deployed within clubs for scouting players, there is little to no evidence of a generative adversarial model being used for the purpose of generating synthetic data for a team to understand where they need to improve. In fact, there is little evidence to suggest that a generative adversarial network model has been used across any industry by reading in data into the generator to create new data from it. Most GANs read in random noise as an input and generate data to pass the discriminator based on an input into the discriminator. So this model is not just restricted to football. This type of model could be used across many industries to improve businesses and increase sale margins and revenue. So there's technologies and techniques. Firstly, we use Python. Python has a clean and readable syntax, which makes it easy to use. It has a large standard library and extensive ecosystem of third-party libraries specifically designed for data analysis, such as NumPy, Pandas, scikit-learn, Keras, and Matplotlib. These libraries provide powerful tools and functions for data manipulation, analysis, and visualization. Python is also extremely useful for reading data from various sources and file types, such as CSV, JSON, or XLSX. Secondly, Jupyter Notebook. Jupyter Notebook provides an interactive computing environment that allows users to write and execute code in a step-by-step manner. It supports the execution of code cells individually, which provides an iterative and exploratory approach to data analysis. You can run code cells out of order, modify and rerun them, and see the results immediately. It is very ideal for data exploration and experimentation, and was good use for the work carried out here. Thirdly, Visual Studio Code. This was used to develop the dashboarding code. VS Code provides excellent integration with Streamlit, a Python library for building interactive web applications and dashboard. You can install Streamlit extensions and plugins in VS Code, which provide features like code snippets, syntax highlighting, and auto-completion specific to Streamlit, making it easier and more convenient to develop Streamlit-based dashboards. Agglomerative clustering produces a hierarchical structure of clusters. This allows you to explore different levels of granularity in the clustering solution. You can choose to cut the clustering granularity at various levels to obtain different numbers of clusters, providing flexibility in analyzing the data at different levels of detail. Another advantage is that there is no need for the number of clusters to be assigned beforehand, as it is an unsupervised clustering method. And the hierarchical nature of the algorithm allows outliers to be separated into their own individual clusters and merged with nearby clusters based on their similarity. This can provide a more robust clustering solution in the presence of noise. This is a factor analysis heat map. So factor analysis determines the relationships between observed variables and latent factors. By plotting the factor loadings on a heat map, you can visually represent the strengths and directions of these relationships. Heat map colors indicate the magnitude of factor loadings, which makes it easy to interpret the importance of variables for each factor. These patterns can offer insights into underlying themes or relationships represented by the factors. Generative adversarial networks model. So GANs are designed so they can learn the underlying data distribution of a given dataset. By training a GAN on a source dataset and using it to generate samples that resemble a target dataset, it is ensured that the generated samples maintain the statistical properties and distributional characteristics of the target dataset. This is advantageous when you want to generate synthetic data that is similar to the target dataset, observing its patterns and structures. By generating synthetic data from a learned GAN model, you can visualize and analyze the generated samples, gaining insight into the data's patterns, correlations, and variations. This can be valuable for understanding the underlying data structure or exploring rare or unusual data instances. And finally, Streamlit. So Streamlit allows for the creation and interactive of dynamic radar plots. You can add user controls such as sliders or drop-down menus to dynamically update the plot based on user input. This interactivity enhances the user experience and enables exploration of different data subsets or scenarios. Streamlit also is specifically designed for Python, making it easy to integrate with popular data manipulation and visualization libraries such as NumPy, Pandas, and Matplotlib. So the results. So this is the original testing data, where a number of teams from the Leicester clusters. And this is a new synthesized data based on the testing data. This output indicates where each team needs to improve to pass the discriminator to be statistically similar to the best teams in Europe. It is clear that the data keeps the relationships and structures between variables and understands to improve certain weak points. Very strong data points may need to drop slightly in order to maximize their potential. And now this leads to this. So finally, a dashboard was created in Streamlit. So this radar plot portrays Burnley's data from the 2021-2022 season. Burnley got relegated from the Premier League that season. The visualization utilizes a radar plot and feature scaling to plot the original data against the synthesized data for each team. This radar plot can be utilized by managers to understand their team's weaknesses and where they need to improve with great intuition. And from here, they can decide if these weaknesses can be resolved within their squad or if they need to look externally in the transfer market to solve these weaknesses. Data gathering, cleaning, and transforming. So two lists are defined, for loop in each elements from the year lists into the URLs, and they are appended to URL list. These lists are then split into segments of 5 to separate each year's URL separately. This function calls each item from the URLs defined and pushes them into a list of lists. This converts these lists of lists into a singular list so that the list has all the team's data from each year. This cleans the messy overhead columns from each year and cleans up the data frames as a whole. So this is the expected output. These lists are then converted into data frames, matching on squad for each year, so all data matches to its squad. So this is the expected output. So data frames with messed up headings or duplicate columns gets fixed and columns get reordered to match each other. It is important to note that FBref changed data provider halfway through the year, so that this function may be outdated as new data was added and columns reordered on the website. So for now, this function is broken, but originally it was working with the original data provided from FBref. So once these data frames are fixed, they're then concatenated using pandas, and this is the expected output. So from df right, duplicate columns are then dropped from the data frame. Wins 1, draws 1, losses 1, and points per match 1 has slightly different data than wins, draws, losses, points per match, so these had to be dropped manually. The df right columns are then renamed to easily understand what each data point means. The columns are then relocated to make a more coherent data set. This is the expected output. From here, the squad and year columns are then combined and the year column is dropped. So this is the expected output. Unwanted columns from this dataset are then dropped. These columns include useless data for in-game analysis, non-insightful in-game analysis data, completed and not attempted data, and data that is already per 90'd. So all of the data is then standardized per 90 using the function. This data is then saved to a CSV file named football data per 90. The same steps are then followed for the validation set, and this validation data is then saved to a CSV file. Now for the analysis. The data is called in. It is assigned to a new variable. This new variable then draws the categorical data so that initial analysis can be carried out. So descriptive analytics is carried out on the data. The columns are set to a variable for exploratory analysis. So the clusters for k-means is defined and a k-means model is fitted to the feature list. The teams are then identified, the clusters are then identified on the teams. So then there's the use of the elbow method. This model finds the optimal value for k. For each number in the range 1 to 8, the number is implemented on the model. Inertia is a sum of square distances between each sample in the dataset and its nearest centroid. These values are appended to the list and implemented on a line graph. As you can see, the elbow crux here of 4. So a standard scalar is defined and the features are converted to a data frame, feeding the scalar on the feature values. These are setting up the variables for hierarchical agglomerative clustering for improvements in k-means and for in-depth analysis. The TSNE library fits a dimensionality reduction technique TSNE on the data to explore the variables. So scatter plot is then defined with colors indicating the league and data points are based from the PCA as shown here. A dendrogram using the PCA data points is then shown for the clustering of teams. Agglomerative clustering model with 4 clusters is then used and the labels are predicted based on the PCA and assigned to a new column in the data frame. So set to label column 2 variables to be called in the updated scatter plot using the PCA data points. The color is determined by the cluster, as shown here below. Factor analysis is computed on the regional features and is fitted on the data. And then a heat map is then provided. A heat map is then provided to show the features that correlate most between the clusters and the data points. The data with the labels is then saved to a new CSV file. This CSV file can then be opened, and you can query the data to show teams based on each cluster to determine which cluster is best. So for example, label 2 contains teams such as Chelsea, Liverpool, Manchester City, Barcelona, Real Madrid, Sevilla, Fiorentina, Inter, Juventus, and Lazio. It is quite clear that based on the other labels compared to this label, that label 2 contains the best teams based off last season with the most superior data. The modeling can now take place. So for pre-processing, the data file is called read in. The squad and league columns are then appended to variables. These variables are then dropped from the initial dataset. The dataset is then split based on the clusters. So the best cluster is all the teams labeled as 2, and the rest of the teams are any data that's labeled not 2. These label columns are then dropped from both datasets. So for training and splitting the data, so X is defined from the synthetic data for training and testing. The data is split into an 80-20 ratio, and the data is scaled using a standard scaler and converted this data into a data frame. The model is then trained. So this model, it defines the generator using 3 layers, all with activation functions leaky ReLU, increasing the units at each layer to learn higher complex relationships between data points. The activation function used is linear, the loss function is mean squared error, and the optimizer used is atom. The discriminator is defined in the exact same way, except that the units defined, they're dropping down by half each layer in order to start at the highest, learning the highest complex relationships and moving down toward an equilibrium as the generator moves up. The activation function remains the same as linear, the loss function remains as mean squared error, and the optimizer remains as atom. The GAN function is then defined from the generator and discriminator with the same loss function of mean squared error and the optimizer atom at a learning rate of 0.0002. So to train the generative adversarial network, the input dimensions, output dimensions are based on the shape from the real data. So the functions are then set to variables to be called. The batch size set to 100 with 1,000 epochs. For each epoch in the range of epochs, a batch of synthetic data is called along with a batch of real data. The discriminator is then trained to understand the differences between the real data and the fake data. The generator is then trained using the lesser team's training data in order to make it similar so that it passes the discriminator model as the real data. So using the same scaler, it transforms the testing data. This is appended back into a data frame. The data frame is then converted into tensors, and new data is generated from the tensors. The scaling is then inversed from the tensors and put back into a data frame to show the results. And these are the results below. To show comparisons, the original testing data is then shown below. And as you can see, average possession has gone higher. Their expected goals has gone higher. Expected non-penalty goals have gone higher. Miscontrols and dispossessions have become lower. And when looked back at the factor analysis, it shows the average possession, expected goals, and non-expected goals to be of very high value. The higher the score, the better. Now to plot the data, so scatter plots are plotted for the original data with their average possession set on the y-axis and all the other columns set on the x-axis. Similarly, average possession for the new data is plotted on the y-axis, and all the other columns are plotted on the x-axis to learn the distributions between the data points. The generator model and the scalar model are then saved into a pickle file. This pickle file is then opened. The generator and the scalar are set to variables. And to validate the data, the Portuguese data is called in. So we call the data for Victoria from the 2021-2022 season. We drop the squad and league values, use the scalar from the saved model to scale the training data. We convert this data to tensors, generate synthetic data using the generator model, and inverse the scaling to get the unscaled synthetic data and convert the data to a data frame to show the results, as shown below here. So originally, Victoria had possession of 48.7%. Now they need to hit 54.7%. And finally, we call in a Streamlit to run this Python file. So this is the dashboarding code. So we use Streamlit for the dashboarding. We set the page configurations, open the pickle file, which contains the generator and the scalar, read in the data that we want to plot in the dashboard, set the generator and scalar to variables, set the squad names to a list, and then create a sidebar for variable selection of each team that they wish to select. The team's data is then assigned to variables, and the dashboard title is set depending on the team name that the user picks. So the categorical values are dropped. The index is then renamed to original data and approved data, as a table will be inputted into the Streamlit dashboard to highlight the metrics themselves. So the column names are defined for the radar plot. A sidebar is then created for variable selection based on metrics that the user wants to see. The values are then extracted from the original data and the synthetic data. The rows are concatenated vertically. And feature scaling is then set based on the maximum value for each data point. So for a radar plot, all the data is on the same scaling magnitude. The data frames are then transposed into rows, and these data frames are then concatenated together vertically. So we assign a number of categories to a variable. The angles for the radar plots are then computed, and to make them circular, they append the first angle at the end. The first value is then repeated at the end to complete the radar plot, and a figure and a polar subplot are created. The values for the original data and the synthetic data are then plotted, and the area is filled between the two lines with colors to show the differences. Then set the tick labels and angles for the categories. So when I run this cell, so the Q&A. So what were the most difficult aspects of the project? Well, probably the most challenging aspect of the project was the initial gathering of the data. There was a lot of organizations, transformations, and cleaning required, with many functions needing to be defined on many URLs to gather all the data and to merge all of this data into a coherent data set for analysis. These functions involved calling of the tables from the URLs and appending them to lists, gathering the list of lists and sorting through them to match up the years for each table. dropping messy overhead columns, appending year and league columns to the datasets, and dropping columns and merging the data frames based on the years together, and fixing up any messy duplicate columns and reorganizing these columns for successful concatenation. So what are the innovative aspects of the project? Well, the most innovative aspect of the project is probably the way the generative adversarial network has been manipulated for its use. To generate synthetic data for teams based on their initial in-game data so that they can understand where to improve to play and compete with the best clubs in Europe in the world of football. From research in the world of football, I cannot find any evidence of such a model being used for this type of analysis and insight. I found this tool to be of great use and one that can be served as extremely useful for club personnel to grow their football club. So how have the objectives changed and what impact did these changes have on completing the project? Well, the initial objective from the midpoint was to build a classification model to successfully group teams based on their in-game data. From here, club personnel could input their team data, see what cluster they sit in and judge how far they are from the next cluster so as to understand how to improve. However, with talks from my supervisor on how to potentially improve this method, how to make it even more intuitive and complete in terms of the full project, a new method was introduced. One that not just told the club what cluster they were in, but told the club exactly how they can improve their in-game play to establish themselves into the best cluster through synthesizing their data based on their current data through the use of a GAN model. This aspect of the project brought more drive, as it's a new technology not previously touched on, and one that seemed very powerful and useful if accurate results could be produced. I feel now, more than ever, that this added model allows for greater completeness of the project and can bring a tool forward that can be of great use in football clubs. So what was the approach to testing? To test the GAN model, I first split the initial dataset into two, one being the team from the best cluster and the other being the rest of the teams. I then split these lesser teams into train and test datasets. The best cluster dataset was labeled as real, and the lesser training dataset was labeled as fake to train the GAN model to produce realistic outputs. The data was scaled using a standard scaler. For testing, the lesser testing data was then scaled based on the initial scaler. This data was fed into the generator model only to produce realistic outputs. The outputs were looking extremely accurate, and while matched against the factor analysis done to understand the variables affecting the cluster the most, the synthetic data scored very high in these variables. Additionally, data from the Portuguese League, which is the 6th best league in Europe, was called in from the 2021-2022 season. This data was set for validation testing after the model and scaler was saved to a pickle file. One team's data was called from the dataset and inputted into the model, and the output again was extremely promising. It showed the model was working well at synthesizing the data and for further validation. When dashboarding the data onto a radar plot, it was validated again to ensure the model was producing promising results. If I was to start the project again, would I change any decisions made and why? Well, if I was to start the project again, I would have taken into account a method used from research I have found that with limited data, when run through the model, the synthesized data produced is added back into the training data and the model is retrained. I found this method to be very interesting, and the results from the paper I have researched named GAN augmentation, augmenting training data using generative adversarial networks by Christopher Bells et al. And the results look very promising. It's something that if I could go back with more time available, it's something that I would like to experiment with to gather more data for training. And finally, this is my showcase poster. So the poster outlines the title, the methodology used, the technologies used, a small description on the models, why data is important in football, as well as some interesting features and plots done throughout the project.